We didn't conquer the moon in 1969, we just visited it as campers. The Apollo missions were monumental achievements, but logistically, they were limited to short, temporary visits to the lunar surface. These early explorers carried every drop of water, every breath of air, and every calorie of food with them from Earth. Once a resource was used, it was discarded, and the mission was over. Artemis changes that timeline completely. With missions 4 and 5, NASA and its partners intend to establish a permanent Artemis base camp at the Lunar South Pole by the end of the 2020s. But building that base means defeating one brutal equation first. Because water is heavy, lifting a single pound of it out of Earth's gravity requires an exponential mass of expensive propellant. Relying on a constant delivery of survival goods from home is a financial dead end. At roughly $93 billion for the initial program, the rocket simply cannot sustain a permanent Earth-reliant logistics chain. So success on the moon demands a closed-loop resource equation instead. Two new rules replace earthbound logistics. Find what we need on the lunar surface and never waste what we find, living off the land. Or in situ resource utilization is the only physical bypass for the rocket equation. And this hunt starts with one rover, Viper. Set for a 2027 launch, Viper will navigate the pitch-black, permanently shadowed craters of Mons Mouton. The rover carries a 1-meter Trident drill to probe the lunar surface for subsurface water ice. Once processed, this ice supplies drinking water and breathable oxygen. Spitting it further creates raw rocket propellant, allowing spacecraft to refuel without Earth's help. Viper isn't just a rover. It's an industrial pathfinder, featuring the initial resource capital required to fuel a permanent human presence in deep space. But finding water is only half the battle. Every single gallon on the moon represents millions of dollars in infrastructure, which means once a resource enters the base, it can never be discarded. At the University of North Dakota, a NASA-built wastewater treatment facility is testing the hardware needed for a bio-regenerative life support system. This system strictly separates waste into 3 streams: solid waste, urine, and gray water. Specialized bioreactors break these down into clean, nutrient-rich feedstocks. The nutrients feed vertical hydroponic gardens, where crops purify the water through transpiration, gathering clean H2O back into a reservoir. This biological recycling loop turns human waste into the metabolic engine of a sustainable off-world ecosystem. Here's the entire Artemis strategy in one line. Viper secures the initial capital from the moon, and bio-regenerative systems keep that capital in circulation indefinitely. And getting this architecture right on the moon isn't optional. A multi-year journey to Mars leaves no room for error or resupply. The loop must be perfect. Solving for survival in the harshest environments of the solar system forces us to innovate at the absolute limits of hyper-efficient sustainability. And these breakthroughs are already finding their way back to Earth. The specialized bioreactors used to separate waste streams in space are being adapted to turn concentrated urban waste into bioplastics for 3D printing, a direct model for circular economies in water-stressed regions on Earth. So the Artemis program leaves behind more than engineering mastery. It leaves a blueprint for the ultimate circular economy needed to protect our homeworld.